about modeling it mathematically and why that's such a hard problem. Several of the speakers have alluded to the fact that modeling and predicting is very hard. Reminds me of that Woody Allen joke. Perhaps it wasn't Woody Allen. You know, predictions are very hard, especially about the future. And this is definitely a good example. I think the first thing, the reason the pandemic is potentially so serious is because it's exponential. And exponential processes are things that we don't have a lot of intuition about. The time that an exponential needs to go from 1 to 1,000 infections is the same time that you need to go from 1,000 to 1,000,000, and the same time you need to go from 1,000,000 to 1,000,000,000. So that's very counterintuitive. And just to give you an example, imagine you want to rent a private island in the Caribbean, and the owner says, I'll give you two choices. You can either pay me 10 million rand a day to rent the house for a month, or you can start off paying me 1 rand on the first day, 2 rand on the second day, 4 on the third, 8 on the fifth, etc. Which would you rather pick? Well, if you choose the first one, where you start off at 1 rand, after the first week, you've paid 250 rand. Seems incredible, a good deal. So which option would you choose? You can think about it a bit, but it turns out that you should definitely rather go for the 10 million rand a day option, because in the first case, you end up spending more than 1 billion rand, and in the second case, you spend 300 million rand. So that's a kind of example of just how counterintuitive exponential processes are. And you'll often hear, perhaps not so often now, but in the early days of the pandemic, people were saying, why are we getting upset? 100 people died today. 1,000 people die every day from cancer, etc. The difference is that cancer isn't an exponentially growing process, whereas pandemics can be. So if we look at daily cases, on the left, you've got daily number of new cases, on the right, daily deaths, and you see that there is indeed this exponential early phase. That's the part that's really scary. And then, fortunately, what we notice is that it transitioned into this much more modest behavior. And of course, understanding that transition is critical to making predictions about how serious this is actually going to be. So I just want to give you some insight into those processes. Well, so how do you model pandemics mathematically? The first thing you have to understand is the progression of the disease. People go from being susceptible, not having the disease, to being exposed, but not yet infectious. They're incubating. And that takes somewhere up to 2 weeks, we think, with COVID. And then they become infectious. And once they're infectious, they can either recover, which is the good route, or they can become seriously ill, at which point they can still recover, or they may die. And so it's sort of a flow. In terms of modeling this, you model it as a flow through these different states. And for example, we use differential equations. You may be familiar with those. Which state tell you how fast, what is the rate of increase of those different categories compared to over time. And so, for example, the rate of increase of infected people depends on the number of people who are infected. The more people who are infected, the more likely you are to get infected. But it also depends on the number of susceptible people. Once you've run out of people who have been infected, there's just no more people to infect. And so the first factor gives you the exponential increase. The second factor gives you what we call herd immunity. So let me just illustrate the first part. So here we have an exponential graph. It just goes straight up, which is basically the point I illustrated. Early on, it doesn't look so bad, but as you scale out, it just goes more and more vertical. And the point is the rate of increase depends on the function. So early times, the rate of increase, which is this line, isn't so bad. You think, yeah, it's just 1 rand a day or 10 rand a day or 20 rand a day. But as you move along, the rate increases. And you can see that as you scale out, this rate, the tangent, is just going to come more and more vertical. And that's the thing that really is so dangerous about exponentials. So we can actually illustrate this quite nicely in a video. So this is a video of someone who built a matchstick model. So here, each match would represent a person. And you can see that at the moment, most of the matches are not alike. Those would be the susceptible people. The matches that are burnt out are the recovered or the dead. And you can see that it's spreading quite slowly at the beginning because there's not much contact between the matches. That models, for example, people wearing masks, not going out, lockdown. But the initial part of the pandemic, when nobody knows about the disease, is very different. There's still a lot of contacts, people are flying internationally, and what you get is this exponentially very rapid spread, okay? And this is the part that was the part that, you know, we were worrying about the whole world, you know, potentially millions of people dying. But after a while, the fire runs out of new matches to set alight, and that's what effectively is what herd immunity is. The question, of course, is for South Africa and for the world is how big is this pile of people that could be infected? What is the level of herd immunity? The simple models predicted about 70%. You would need to infect 70% of people before the pandemic kind of starts to peter out. But other models suggest maybe it could be lower. And that's an example of what makes it so hard to model. So we can build models, but are they right? For example, we don't yet understand the disease fully. What is the mortality rate? Is the asymptomatic fraction age dependent? It could be that we know that very few children die, but there's indications that they are as infectious as adults. So looking at the number of children who die is not a useful thing to do if you're worried about old people dying because they may be infected. There's also so many things that we can't know yet. For example, we don't know how many infections we're missing. Are we missing 50%, 80%, 99% of the infections? We don't know how many deaths we're missing. For example, right now, there's supposedly just 5,000 or so deaths, but the excess mortality is over 17,000. We don't know how people will react. We don't know what the effect of weather will be. We don't know the effect of how bad will winter be. Will it be very cold? So far in the Western Cape, we've been very lucky. It's been a beautiful winter. We don't know whether blood type is important, whether the disease will mutate, whether BCG vaccinations, etc. It's just a huge amount that we don't know. And that does make predictions very hard. And so whenever you see someone make a prediction, you should be very skeptical because there's just so much we don't know. So here's an example from a researcher at UWC who put out a model on June the 30th for South Africa looking at daily deaths, and their model, which seemed to fit the data beautifully, predicted that everything would get better after the end of June. And then by now, mid-July, we would be down at about 40 deaths per day. Of course, yesterday we had 250 deaths. We're actually completely off this chart. And yet, if you just looked at the past data, you would think this is a beautiful model. It's definitely going to be right. So, you know, it's important. I love this quote by George Box. He said, all models are wrong, but some are useful. And in pandemics, it's actually very difficult to know ahead of time whether your model is useful or not. This model looked useful, turned out to be completely useless. So in our own modeling, which is part of the National Ventilator Project for supplying, we are trying to do predictions of how many ventilators will South Africa need. Instead, we chose to try to run thousands of models. And you can see each curve here is a different model representing a possible scenario. So up here is the number of deaths versus time. This is days. The x-axis is the number of days since the 1st of April. We did these forecasts at the end of April or perhaps end of May. I can't exactly remember. And you can see we predict that there are models with just a few thousand deaths all the way up to models with hundreds of thousands of deaths. In black is the actual deaths. Now, the problem is I can't tell you whether these models up here are more or less likely than the models down here. All I can tell you is that depending on how things roll out, these models are possible. Fortunately, now if we go and redo this analysis, I would say we are more likely to be living under the white line than above it, but I wouldn't bet my life on it. There are just still so many uncertainties. Okay, so there are people who have argued, Michelle alluded to it, saying we will definitely not have more than 20,000 deaths. We already, I think, have 17,000 deaths. So I think that is overly hopeful, but it would be great if that turned out to be true. But this is just an inkling of the complexity of trying to model this. It's a little bit like trying to predict the weather 6 months from now. Very, very challenging. Anyway, so if you're interested, we have released our reports and our code. You can go and play with it, and you can run your own forecasts. But yeah, I think I'll stop there. Thank you so much.